Hello everyone, thanks for watching. I'm León and I will be talking about work that combines reinforcement learning with classical strips-like planning. As is usual, this work is done with collaborators, Rodrigo and Sheila. We're all at the University of Toronto and at the Vector Institute, and Sheila is a CFAR AI chair. As I said, the paper I'm presenting here is about a combination of planning and reinforcement learning. And the reason for this combination, the endeavor that we set out to address, is that we want to be able to tell an RL agent that we want it to do some task and then just have it solve it. I want to be able to tell my block stacking robot, build me a stack of blocks A, B, and C in that order, please, and then see how the robot does it. This is what we do in planning. And I don't want to have to sit around playing with the robot and the blocks for a few years before it can solve the task, right? I mean, I'm happy to do it with my kids, but maybe not with a robot. Of course, we think the combination of RL and planning is a good approach for this problem, but it's okay to ask why, right? So, why use RL? I don't think I need a lot of effort to convince most of you that reinforcement learning is great. If you've paid any attention to it in the past 5 years or so, you will have seen impressive results: board games, video games, robotics, and more. And all of this is without need for an explicit model of the environment. In most cases, it's actually model-free RL, without need for even learning a model. However, reinforcement learning hasn't actually taken over the industries of optimization. Yeah? There's some use in robotics, some use in finance, but few great real-world success stories. An obvious reason for that is that RL can be very inefficient, actually. Especially when rewards are sparse. For example, AlphaZero had to play about 20 million games of chess before playing at the level of the Stockfish engine. A less obvious reason is that it can be hard to get an RL agent to actually optimize for what you want. Someone, I won't name names, if you know, called this the dirty secret of RL, that if you want to apply it, someone needs to program the reward function. AI planning, on the other hand, has almost the opposite set of virtues and vices. Modern planners are really very efficient, and once you have a model, specifying a new task that tells the agent what you want is almost trivial, right? Of course, this is just sort of shifting the goalposts, really. Now, instead of programming a reward function, I'm asking you to program a model of the environment where defining the reward function that you want is actually easy. And this brings us to what we actually did, which is a very simple idea. We define high-level planning models that are just very coarse, abstract representations of the real environments. This shouldn't be hard to do. And then we can use reinforcement learning to deal with all the messy low-level details that these models omit. This is hopefully a best of both worlds approach that lets us easily define tasks as high-level goals, and this doesn't even have to be done by the same people that design the model. So you can give this to an end user that doesn't need to know anything about RL or reward functions. Beyond all that, we can also use the models to compute plans, which in turn can be used to guide the RL algorithms, which should lead to significant efficiency improvements. So the contributions of the paper are that we defined a new type of RL problem, which we call taskable RL, in which low-level environments are augmented to include high-level symbols. We designed and built a system that leverages the symbolic information by exploiting handcrafted models of high-level actions. And here we use the high-level actions to identify useful options for hierarchical RL. Options are like high-level skills or macro actions that can be learned and reused in multiple places or across different tasks. Then we use high-level plans as instructions in order to improve on sample efficiency. Finally, we also show that this is theoretically correct when the models satisfy a notion of consistency with the environment and provide some experimental validation. In the next few slides, I'll show you how taskable RL is actually formalized, how we use the high-level plans, some issues that arise when we do, and how we palliate those, and a brief summary of our more interesting experimental results. Formally, a taskable RL environment is defined as an extension of a Markov decision process. As usual, S is a set of states, A is a set of actions, R is a reward function, P is the transition probability distribution, and gamma is the discount factor. In addition to all that, we have a set of propositions, capital P, a labeling function L that assigns sets of propositions to states, and a goal reward parameter R, which represents the additional reward given when a task is solved. Now, a task can be given as a set of propositions which represents a final state goal property. The agent's objective then is to reach a state that has those propositions as part of its label. Finally, we get to what is essentially the outline of our main algorithm. Given a high-level model and a specified task, we can find a plan. Given this plan, we can try to execute it. This means that we need to learn low-level policies for the actions in the plan. Effectively, this is a form of hierarchical reinforcement learning where we already have a high-level policy, the meta-controller. It's the plan. So going on to solve our first task ever with this, we only need to learn policies for each of the high-level actions in the plan, or the options. This means we won't immediately be able to solve the task, of course, but the decomposition makes it more efficient than solving the task without the plan. And as life goes on for this RL agent, things should get better and better. The action policies will eventually stabilize to optimality, and new tasks should be solved immediately. There are still, however, some issues that arise. The first is that by baking in all this structure, we restrict the space of valid solutions, so we may be incapable of actually reaching the optimal solution. This is already an issue in hierarchical RL, but we're making it even worse here. We can make it less of an issue, however, by relaxing the high-level plans into partial order plans, and then learning how to best order them as we go. Obviously, this means we need to do more learning than before, but that we will be able to find better solutions. On the other hand, we can't always assume that the models are a reasonable representation of the low-level environments. And what this means is that eventually we will see that some actions may be impossible to properly realize or that they may have unintended side effects. We have a first approach for dealing with these that uses execution monitoring techniques, where we look at the state after we execute a high-level action and verify that it's roughly what we expected, and that if there's differences, these are not going to be an issue later on, or that if they are, then we can figure out what to do instead, right? Now, of course, you should be asking whether or not this works and how well and so on. So here is an example environment, and I'll show you some results in a minute. The idea is here, this is an office environment represented as a grid world. The robot, the RL agent, can start in any cell and can move step by step in any of the 4 cardinal directions, and that has a cost of 1. An example tasks here may be to go get the coffee or go get the mail and bring it to the office where the purple hand is, or to visit locations A, B, C, or D, and any combination of those. Right? For our experimental setup, what we did was use different RL algorithms that may or may not use the additional information from the model and from the plans, and we sequentially give them 4 tasks in increasing order of complexity. So first we train and evaluate on task 1, say, for 5 million training steps, then task 2, and so on. The idea is to validate that by giving the agent access to the additional information in the high-level model and the plans, it will be able to find good solutions faster and will be able to transfer more of what it learned in the first tasks to the later tasks. As a baseline, here you can see what happens when we train with the basic Q-learning algorithm. In the x-axis, the plot shows the number of training steps, and you can see the 4 tasks aligned sequentially. The y-axis has the average reward obtained by a policy that has been trained for the corresponding number of steps. As you can see, task 1 is easy to solve, and the other tasks get harder and harder. Q-learning does not exploit the symbolic models at all, and cannot reuse any information from one task to the next. It does, however, converge to optimality in all cases. If we use hierarchical RL, taking advantage of the options identified in the high-level models, we see that even though we don't quite converge to optimality, the early performance is, in all cases, significantly better. This is particularly noticeable in the harder tasks, where we get to take advantage of the policies for the high-level actions learned in the previous tasks. Now, if instead we force the robot to follow a high-level plan, we see some very impressive results. Here, it almost immediately converges to a good solution. There is still an important optimality gap, but the robot is actually solving the harder tasks with almost no additional training. The solutions are not optimal, but they are correct solutions to the specified tasks. And finally, we can get slightly better results at almost no additional training by using the partial order plans instead of sequential plans. We also have other experiments where we can see that the issues I have mentioned can be important and hard to address. Here we have experiments in a 2-dimensional Minecraft-inspired environment, which is similar to the office world, but much more complex. It's still a grid world where the agent moves and collects objects, but here the objects represent resources that can be spent in order to produce other objects. As you can see, most of the algorithms we tried don't seem to reach useful policies for the hard tasks. The issue here is that our model is actually inconsistent with the environment. While you're out with some wood and iron ore trying to make a hammer, for example, you may end up unintentionally building an axe if you happen to be at the wrong place. And this is not at all reflected in the high-level actions. We tried some execution monitoring techniques here, and it does improve the quality a bit, but not quite enough to say that that is the right approach. At this point, I think future work should probably focus on updating and learning better models. So, to summarize, the main contributions of our paper are the definition of taskable reinforcement learning, which is a new type of RL problem that focuses on having the possibility of easily specifying new tasks for an environment. We also built a system that leverages high-level symbolic models for better efficiency and transfer learning. And finally, the main takeaway message is that this actually works. It's not hard to use, and it can take advantage of new and future advances in both model-free RL and planning, which is always a good thing. Thank you. If you're watching this live, we should now have a few minutes for questions.